The metric tensor, based on the absolute foundation of the constancy of the speed of light, we've established the spacetime interval ds squared. It is also referred to as the line element. The line element is constructed upon the introduction of four-dimensional spacetime, which unifies space and time and carries the dimension of distance, a universally accepted concept. This is what we have obtained. While ds squared is an invariant physical quantity when expressed in coordinates, the value of ds squared must remain unchanged regardless of which coordinate system we choose. What is it that keeps the line element invariant? What plays the role of preserving the invariance of the line element? That is the metric tensor. In fact, this metric serves as a compass that preserves the invariance of the line element even in the curved spacetime of general relativity. Since ds squared is an invariant quantity independent of the coordinate system, let us explore its structure using the intuitive setting of two-dimensional Euclidean space. We will proceed by comparing Cartesian and polar coordinates. First, we will derive the metric and the line element ds squared in two-dimensional Cartesian coordinates. The infinitesimal position vector is expressed using components and basis vectors as. In Euclidean space, the line element ds squared represents the spatial distance and is calculated as the inner product of the infinitesimal displacement vector with itself. Looking at the form of this expression, we can see that the combinations of infinitesimal displacements and inner products of basis vectors are systematically arranged. The inner products of the basis vectors appearing in this expression are called the metric tensor and are expressed as follows. Expressing the line element ds squared using the metric and components. Since Cartesian coordinates form an orthonormal basis, we now substitute the components of these metric tensors into the expression for ds squared the Pythagorean theorem has emerged. We have obtained the line element and metric of the two-dimensional Cartesian coordinate system. Next, we will generalize this so that it can be used in any coordinate system. Since this is two-dimensional, there are two coordinate values, x and y. We express x as x superscript 1 and y as x superscript 2, where the superscripts denote the coordinate indices. For the metric, we use index 1 for x and index 2 for y. When we express the line element using this method, when we express the equation in this form, it can be written using the summation symbol sigma as follows. The metric gij with lower indices and dxi dxj with upper indices share the same index values, enabling us to express this compactly as a single summation. These upper and lower indices carry deep physical significance, which we will explore when we study general relativity. Now, Einstein came up with something even more remarkable, which he jokingly called the greatest discovery of his life. His idea was this: whenever the same index appears as both an upper and lower index in a single term, we can omit the sigma symbol altogether. This convention allows us to simplify equations even further into an elegant form, without any loss of mathematical rigor. This is called the Einstein summation convention. Generalization of the line element using Einstein summation convention. line element, and metric in polar coordinates. Now let us apply the generalized line element formula to derive the line element and metric for two-dimensional polar coordinates. The coordinate values in polar coordinates are r and theta, so we set dr equals dx superscript 1 and d theta equals dx superscript 2. We assign index 1 to r and index 2 to theta. Since the metric components are defined as inner products of basis vectors, we obtain Recall that the basis vectors in polar coordinates are given by substituting these into our metric formula. Since the Cartesian basis is orthonormal, this section involves calculation. Please pause the video and work through it at your own pace. These are the metric components in polar coordinates. Now that we have the metric, let's substitute it into the generalized line element formula. This gives us the line element in polar coordinates. We have derived the line elements and metrics for two-dimensional Cartesian and polar coordinates. We can see that the metric appears as the coefficients in each coordinate system. The line element takes exactly the same form in each system. To distinguish between different coordinate systems, let us add a prime to one of them. Since the line element is invariant, these two expressions are connected by an equality. Supplementary note: this section involves calculation, so please pause the video or skip ahead if you prefer. This mathematical form holds not only for Cartesian and polar coordinates, but extends to 3 dimensions, 4 dimensions, and even arbitrary n dimensions. Furthermore, it is expressed in exactly the same form not only in inertial frames, but also in the curved spacetime of general relativity. This property is called general covariance. Although coordinate values and basis vectors differ between coordinate systems, the metric serves to absorb these differences and preserve the invariance of the line element ds squared. Metric of Minkowski spacetime. We derive the metric of Minkowski spacetime. The coordinates are ct, x, y, z, starting from the equation for the line element with general covariance. In 4-dimensional spacetime, Greek indices are conventionally used. For Minkowski spacetime, the metric is specially denoted by eta rather than g. Thus, we rewrite the line element as the metric is the inner product of the basis vectors in the coordinate system. Therefore, the basis vectors of Minkowski spacetime are e subscript t, e subscript x, e subscript y, and e subscript z, corresponding to the coordinates ct, x, y, and z. To write this compactly using Einstein's summation convention, we relabel c dt, dx, dy, dz as dx superscript 0, dx superscript 1, dx superscript 2, dx superscript 3, where the indices 0, 1, 2, 3 correspond to ct, x, y, and z respectively. This gives we compare the line element of Minkowski spacetime with this expanded equation. The coefficients of dx mu dx nu represent the metric components, so the non-zero components are The metric components are the coefficients of dx mu dx nu and represent the inner products of basis vectors. Therefore, the negative sign for the time component arises from the derivation and fundamental properties of Minkowski spacetime. Recall that we derived the line element from the spherical wave equation, and that in Minkowski spacetime, the line element can be positive, negative, or zero. Matrix form of the Minkowski line element. Let's express the Minkowski line element in matrix form. Expanding the Einstein summation convention explicitly, we get, in matrix notation, this becomes recall that dx0, dx1, dx2, dx3 equals c dt, dx, dy, dz, and eta with lower index 0, 0 equals -1, eta with lower index 1, 1 equals 1, eta with lower index 2, 2 equals 1, eta with lower index 3, 3 equals 1, all others 0. We obtain Let me add a brief note about the metric eta mu nu, as we'll need this later. This is written with lower indices, but there also exists a version with upper indices, eta mu nu. When we contract these, multiply and sum over indices, we obtain the identity matrix. For Minkowski spacetime specifically, eta mu nu has the same form as eta mu nu. The reason why this is true will become clear when we study general relativity.